Hi, my name is Ciro Lima. I work at the Instituto de Pesquisas Eldorado in Design House Department. This presentation is about the article A Functional Verification of a Multi-Rate FSK Modem Compliant to IEEE 802.15.4g, written by Ciro Lima, Daniel Urdaneta, and Eduardo Lima from Instituto de Pesquisas Eldorado. Introduction. A brief overview of WISUN. Wireless Smart Ubiquitous Network WISUN is a technology based on IEEE 802.15.4g, promoted by WISUN Alliance, a global organization created in 2011 to endorse the adoption of a smart utility network as detailed in IEEE 802.15.4g. With the purpose of leading the challenge to optimize and automate metering, control, and monitoring, WISUN Alliance is driving smart ubiquitous IoT network applications. The WISUN technology provides some advantage like low latency and high data rates that are consistent throughout the network, support to IPv6 protocols, and support to mesh network scaling capacity and size. A brief overview of the IEEE 802.15.4g. This is an amendment of the IEEE 802.15.4 that defines the physical and media access control layers. The standard feature is low-rate wireless connectivity with low power consumption and short-range communication. Every PI in the standard tackles three operation modes: the MR-OKPSK, the MR-OFDM, and the MR-FSK. This work focuses on the functional verification of an integrated circuit MR-FSK PI. Some advantage of MR-FSK PI: transmit power efficiency due to the constant envelope of the transmit signal, low implementation complexity. Features. Here are the features of the MR-FSK covered in this verification: 14 frequencies, 3 operating modes, covering data rates from 2.4 up to 200 kilobits per second. There is a force operation mode in the two regions of Japan that use a 400 kilobits per second, but both in 4 FSK. 2 FSK and 2 GFSK, modulation and demodulation. The 4 FSK functionality is being implemented in design. 4 error correction with 2 types, RRC and NRNC. Code symbol interleaving and interleaving, data whitening and dewhitening, switch mode, demodulation with AWGN channel, and test mode. The methodology used for the functional verification of the MR-FSK PI is coverage-driven with constraint random based using system Verilog. Other methodologies such as UVM could be used. However, the MR-FSK is a block that will be integrated into another system and doesn't need complex agents. All the configuration is made directly in the input ports and doesn't have internal registers. No need of UVM register layer. The class developed for this test bench can be easily usable in a UVM environment. Another methodology is formal verification using Cadence Jasper Gold. Although it's not being used in this project, the possibility of using it is considered. Some MR-FSK blocks of the modulator and demodulator were also tested in a separate test bench and performed sanity checks to avoid bugs after the integration. Also, some MATLAB models were developed to test some functionalities. Tools used: Cadence Chiselium Logic Simulation, MATLAB R2015A, Cadence SimVision, Incisive Metric Centers to analyze the report coverage. Stimulus. This is the format of the frame that is the stimulus for the MR-FSK. The SHR is composed by the preamble and SFD. The preamble is a 8-bit sequence that repeats according to the number of octets configured. The SFD has 4 possible values, depending on if it is encoded or not. The PHR is a 16-bit number with configurations of the mode switch, data whitening, and frame length that defines the number of octets of the PSDU. The PSDU has a variable length and range from 4 up to 2048 octets. Block diagram and flowchart of the modulator. The block diagram is better explained looking at the flowchart below. Receiving a start signal, the system creates the PI protocol data unit, the PPDU. First, PHR and PSDU are concatenated. Then, the use of FAC for that frame is checked, and the data processing is applied accordingly. The same process is done for interleaving and data whitening, except whitening is only applied to PSDU. After data processing is done, STR is concatenated and the complete frame results in the modulated signal. The FSK is used to control errors in that data transmission. Two types of FSK can be used, the recursive and systematic code RSC or a non-systematic code NSC, depending on which one was chosen previously. The interleaver is used to improve performance of forward error correction codes, creating a more uniform distribution of errors. And the whitener is intended to randomize the data payload, avoiding the presence of long sequence of bits with the same value. Block diagram and flowchart of the demodulator. Signal demodulation starts by reading the modulated signal from transmission. The demodulator can be selected between FSK or GFSK. Once the data bits are retrieved, frame header SHR is detected, the limiting frame starting point and extracting SHR parameters needed for internal control, like FSK and interleaving enable parameters. Once PHR and PSDU are extracted, the first one bypasses the data whitening and is processed by the remaining enabled data processing blocks. Once PHR is parsed, PSDU can continue on the data path, passing through data whitening, if applicable, FSK and interleaver. At the end of receiving process, the PSDU goes to the serial output of receiver. Block verification, FSK encoder-decoder. This is one of the integrated RTL blocks of MRFSK that were tested in a separated test bench. The data path starts with a random stimulus being applied in the FSK encoder and forwarded to the serializer that stores it in a system Verilog GUI. The random stimulus is also sent to the predictor that has the FSK modeled in MATLAB. The monitor reads the FSK output and sends to the checker and compares data processed from the predictor with data received from monitor. The checker also compares the stimulus sent in the FSK input with the output of FSK decoder. Also, a touch bench with only the demodulator and its sampling implemented in RTL were instantiated to verify the demodulator performance. Verification environment. Here is an overview of the top test bench. The DUV comprised the MRFSK with a resampler and FIFOs implemented in RTL. The resample is connected between DUV and the interface to connect the sampling of different transmit data rates to 20 samples per symbol in the demodulator input. FSK interface is a system Verilog component that connects RTL with the test bench, which encapsulates the signals and has clocking blocks implemented. There are two drivers for transmitter, one to configure the DUV's inputs and another to send the PSDU to the serial input interface. There is one driver for the receiver that reads data sampled stored in queues or reads from files when the MATLAB models are required. One driver for the receiver that reads data from the file or FIFOs and sends the signal collected from the transmitter output to the interface and resample. A monitor that reads the transmitter output demodulates the real and imaginary parts of the signal and sends to the scoreboard. It also stores the data in files. And a monitor that collects the demodulated PSDU in the serial output of the receiver. A coverage collector that samples the functional coverage in each test. The predictor that mounts the frame without modulation and the PSDU expected. And the scoreboard that receives data from predictor and the monitors. Here are some details about the class that configures the DUV, the class FSK configuration. It has random attributes and attributes that have default values. Real number attributes to perform real calculations. It has attributes to set random PSDU or not. It receives the frequency sampling from the test bench and reconfigures all the attributes. It also sets a random seed to pass the MATLAB script to the AWGN function. Below is a piece of code of a function that sets data rate and its real values based on the frequency band and operation mode set in the test. This is another example of some calculations in real number to set number of samples to the transmitter and receiver, a frequency ratio to the resampler, and converts it to the fixed point to set DUV's inputs. Below, some attributes with constrained randomization. Modeling. The models were implemented in MATLAB and System-Verilog, and it is used to predict the PPDU without modulation based on the configuration set in the beginning of each sequence. It only predicts the transmitter outputs to find bugs earlier before being processed in the receiver. The samples collected from the transmitter outputs are demodulated in a MATLAB script and returns a string with the complete frame that is compared in the scoreboard with the PPDU predicted. When FAC encoder, whitening, and interleaving are required, it uses MATLAB to mount the string, otherwise it uses the models in System-Verilog. Coverage. Here show the implementation of the cover groups with cover points for each functionality, and the report of incisive metric centers for one test executed. Here is a basic sequence of the transmission and receiving of a complete frame. In the frame transmission, the PSDU is sent through the serial input and all the signals in the transmitter outputs are stored. In frame reception, the receiver is enabled and the driver starts to read the signals previously stored and send them to the receiver inputs. The PSDU demodulator is read in the test bench from the receiver output. This sequence repeats over and over until reach the number of bits to be transmitted. The beginning of the waveform is the transmission of the PSDU in the serial input, as is shown in the next slide. Here is an amplified view of the previous slide. The communication between the driver and the DUV is done using the valid read protocol. The PHR read input of the DUV starts asserted and the driver asserts the PHR valid input, indicating that all data configuration in DUV's input is valid. After, the PSDU is sent on the next cycle, whenever the PSDU in read output is high. Here is an example of how the test bench is interacting with MATLAB. The System-Verilog utility $system allows executing of a command on the Unix shell whenever is needed. This piece of code shows the part of the test that is required an AWGN insertion in the output signal of the modulator, stored in files. Instead of write AWGN algorithms in System-Verilog, it's very simple to process using the AWGN MATLAB function. Basically, the string passed is formed with local of MATLAB execution, some directive to run MATLAB completely quiet, and the name of the script to run. Some value generated in test bench can also be passed to MATLAB script. The script reads, processes, and stores the data files, return the control to test bench, and continue the simulation without user intervention. To run a specific test, the test name is passed in a string at runtime from the makefile to the test bench. This is made by using $value $+args System-Verilog utility. It allows to run multiple tests at the same time depending on the maximum number of tool licenses available. Test folder structure and organization. To make possible to run multiple tests at the same time was created a directory structure with folders for each test. This structure is created using a Python script. Each folder contains data files from simulation, logs, MATLAB scripts, and the coverage collected. Another script makes the merge of the coverage for each folder. To run performance tests, we created direct tests to set frequency, operation mode, and modulation scheme, keeping the randomization just for PSDU data and the AWGN seed. The noise is placed only in the PSDU. Then, the MATLAB script analyzes the maximum absolute value of the peak in the real and imaginary parts of the signal and divides all samples by this value, making it possible to send the signal without clipping the demodulator input. This process is made for each ABN0 value. Using the internal synchronizer of the receiver, it's necessary to adjust the threshold correlation for every noise level, and it's difficult to find the optimum values for the synchronizer to provide a good data rate clock to the demodulator, resulting in the loss of package and make a new attempt to send another. To solve this problem, an external data rate clock is provided from the test bench to the demodulator, and the synchronizer is disabled. This clock is active only in the reception of the signal. A state machine in the test bench analyzes when the receiver is enabled and the start of the signal, giving the best position for the demodulation. Configurations that have low data rates such as 2.4 or 4.8 kilobits per second in the simulation take several hours to run just one point of bear. To speed up the simulation, it's possible to change the frequency sampling of the system and passing the new value to the configuration object. Then, all the parameters are reconfigured with the new values. Tests that last 10 hours can be executed in less than an hour, just decreasing the frequency sampling. Here are the bare results for FSK demodulation on the region of US and Canada using 10 frames of 1050 octets, giving the total of 100,000 bits transmitted. Consider that all data rates in this region use a modulation index of 0.5. The results are very closer for the three data rates, 10, 20, and 40 kilobits per second. The graphic below is of the worldwide region. The green line is the theoretical bar for modulation index of 1.0, that is close to the 50 kilobits per second. The other two data rates in this region use a modulation index of 0.5, and the theoretical bar is not shown. Data rates higher than 50 kilobits per second have some degradation due to the filter used that limits the noise up to 50 kHz. The results of the GFSK bar for worldwide and China. The curves are a little bit far from the expected, showing green line, but we are making improvements in the demodulator to reach better performance. Although some of the RTL of the MRFSK is being modified and improved, the gate level simulation will be performed after a final release of the synthesized RTL. The netlist that will be used is a wire load model using a CMOS library in 65 nanometers from TSMC. The netlist used for gate level simulation is for the typical case and the PVT conditions of 1.20 volts in 55 Celsius. As the gate level simulation takes a long time, no need to run regression tests, considering that exhaustive tests were previously run. Then, just initialization and reset tests, sanity checks for each functionality, and reduced frame length will be executed. Conclusions. 4-level FSK and GFSK modulator and demodulator are in development. We are making improvements in the demodulator to reach better performance. Validation in FPGA were previously tested, but need to remake the tests again. The MRFSK is a part of a system integrated with OFDM and other blocks. Possible use of formal verification using Jasper Gold. Thank you.